Okay, welcome back. What I want to look at today is monostable multivibrator circuit. Now, the monostable multivibrator circuit can be used to output a given waveform or a signal, okay? But once you have read the information and seen the diagram for yourself, do some research for yourselves. Get to know exactly what it is that the monostable multivibrator does and where it can be used, other than what I have shown you. Now acquire some knowledge of your own. Now here you'll see that I have taken the opportunity of showing you the diagrams first before I went into any text. So here, sorry, let me just bring the diagram up a bit more clearer. Now here you'll see I've simply put it as diagram MV, monostable multivibrator 1, okay? Now I'm just going to go up so we get it in full view and in full sight. Okay, that's good. Now here you'll see I've taken this base biasing resistor RT, and I've become here now. That's the base biasing resistor. Now excuse the old-fashioned type of resistors, okay, but it's just the way it was done then. Okay, and this is your base biasing resistor. Now what this does, this provides a source of current to the base of TR2 by triggering the base of TR2 just slightly to come on. It causes a current to flow. Now I'm just going a little bit further as well. Now here you'll see time constant and output unstable state. Okay, now it's the monostable multivibrator actually switches on and off, or you can have two LEDs which will be flashing basically synchronously, one on, one off, and that's what we're looking at. The time constant, now T equals C times R if I remember correctly, but please check that up for yourselves. I'm just doing this from memory at the moment, and sometimes my memory fails me all the time, so please do forgive me. Okay. Right, now this is your VCC rail, that's your, just call it your positive rail. Okay, and somewhere down here would be a negative rail, which we can set down as your negative or ground. Now here, bear with me again while I go up a little bit more. Now here we have R1 and R2, but for some reason in my mind I would have called this R2 basically, and you will see that I've made a mention of it in the text further down, but let's continue to treat this as RT, okay? And you'll see that it's at a value of 120,000 ohms. R1 is 10 kilo ohms, which means 10,000 ohms. R2 is also 10 kilo ohms, okay, 10,000 ohms, and that is the resistance. What this does, it allows a potential to be developed at the collector stage of the transistor. Okay. Let's take it down now. Here we have the collector of the transistor. You have the emitter, okay, of your transistor, and you have the base of your transistor. And this applies to both transistors. So I only need to write this down once, okay? It does not change. And these are NPN type transistors. I should have written that in somewhere along. Oh yes, I have. Yes, yes I have. These are NPN type transistors. Okay, I'm just moving so you can see that there for yourself. Okay, come back out a little bit more. Okay, NPN transistors. And we can tell that because the arrow points outwards. Okay, we won't go into anything else further for other type of transistors, but this is NPN transistors. Now this diode here with the capacitor allows you to keeps the input constant or smooth, and it acts as a trigger. This diode here only trigger in one direction. It will not allow any current to come in the reverse direction. So once you apply your input here, you can be sure that input will have an effect on your transistor. Nothing else is going to change it. Nothing else can come through from that direction. It will only flow in that direction. Okay. Now let's look at what we're trying to say here now. The basic collector coupled transistor, monostable multivibrator circuit, and its associated waveforms are shown in the above diagram in V1. Now always look back at the diagram so you know what it's trying to tell you about. Okay, and look at how the relevant capacitors, the relevant resistors, and where they are located. Okay. Now this capacitor here would be an electrolytic capacitor, but I'm surprised that they've not put it in a different manner, simply because this side here has indicated a positive, so it will be an electrolytic capacitor. Okay, because it is polarity sensitive. That's the word I was looking for. Okay, so let's get back to the text. Now when power is firstly applied, the base of transistor TR2 is connected to VCC, and we have identified where VCC is already, and VCC is here. That is your VCC. Okay, it means the positive rail. You see, via the biasing resistor RT. This resistor could be labeled R2, as I mentioned earlier, okay? But it's not. It's RT, so treat it as RT. It was just my fault that it could have been better explained. But we'll run it as it is, thereby turning the transistor fully on and into saturation, and at the same time turning TR1 off in the process. Okay. Okay, good. This then represents the circuit's stable state with zero output. Now the current flowing into the saturated base terminal of TR2 will therefore be equal to VCC minus 0.7 divided by RT. Now RT is the value of the resistance, so let's go back and look at RT. Okay, so we know which RT we're talking about, and that is RT, and we know RT is 120,000 ohms, 120k ohms if you prefer. Okay. So again, when power is firstly applied, the base of transistor TR2 is connected to VCC via the biasing resistor RT, okay, thereby turning the transistor fully on and into saturation, and at the same time turning TR1 off in the process. This then represents the circuit's stable state with zero output. The current flowing into the saturated base terminal of TR2 will therefore be equal to IB equals VCC minus 0.7 over RT. Now 0.7 is the voltage which the transistor will operate at. Okay, that's the okay. Okay, I'm just trying to make sure that I've got this online and I can get it all in. So bear with me for a moment. Over RT. Now ignore R2 because it's only me putting this bit in as an R2, but it's not R2. Treat it as RT. R2 you can ignore in this case because R2 there is actually the other resistor. So let me make sure that we are quite clear on this. This resistor here will be R2. This resistor here, RT, should remain as RT. For some reason, I try to refer to this as R2, but it's not. Treat it as RT. Okay? I did that for a reason earlier when I did other circuits, because it made more sense at the time. Okay? But look at this now, I can see that it can be a bit confusing. So, treat it simply IB equals VCC minus 0.7, not over RT. Okay? Just ignore the R2 because it is not R2, it remains RT. Please note this is simply the formula you would apply to find the current of IB, having been given a VC voltage and an RT or R2 values. Okay. Now, if a negative trigger pulse is now applied at the input, the fast decaying edge of the pulse will pass straight through capacitor C1 to the base of transistor TR1 via the blocking diode turning it on. Now, it is important to remember that the triggering will only trigger on the falling edge. It will be triggered on the falling edge of the pulse. Okay? And again, let's look at where C1 is. And that is C1 here. Okay? And that is your blocking diode. Now again, just to recap, if a negative trigger pulse is now applied at the input, the fast decaying edge of the pulse will pass straight through capacitor C1 to the base of transistor TR1 via the blocking diode turning it on. Okay? Now, the collector of TR1, which was previously at VCC, drops quickly to below 0 volts, effectively giving capacitor CT a reserve charge of 0.7 volts across its plates. This action results in transistor TR2 now having a minus base voltage at point X, holding the transistor fully off. This then represents the circuit's second state, the unstable state, with an output voltage equal to VCC. Now remember, the output voltage for VCC will be the applied voltage what you have used. So if you have been using a 9-volt battery, then the VCC will be 9 volts. Okay. Timing capacitor CT begins to discharge this 0.7 through the timing resistor RT, attempting to charge up to the supply voltage VCC. Now again, .7 volts, if I remember correctly, it's the voltage you will have across your resistor. Okay. Now this negative voltage at the base of TR2 begins to decrease gradually at a rate determined by the time constant of the RT-CT combination. Okay. As the base voltage of TR2 increases back up to VCC, the transistor begins to conduct, and in so doing turns off TR1 again, which results in the monostable multivibrator automatically returning to its original state, to its original stable state, awaiting a second negative trigger pulse to restart the process all over again. Okay. So you can actually slow this down by varying the rate of the time constant, and you can trigger that at your own pace. But remember also that you can also increase the rate such that it is almost the LEDs, and that we would normally use LEDs, would appear to be constantly on once the cycle was consistent and rapid enough, I should say. Monostable multivibrators can produce a very short pulse or a much longer rectangular shaped waveform whose leading edge rises in time with the externally applied trigger pulse, and whose trailing edge is dependent upon the RC time constant of the feedback components used. So I am right. Time constant it is to do with the RC circuit. Okay, but we're not doing that here. All I'm doing now is to provide you with some information that you can apply or be aware of in due course. Okay. As a matter of fact, I think I may have done time constant in one of the videos previously as well. If I haven't, I will make my business to try and get that in due course. Now this RC time constant may be varied with time to produce a series of pulses which have a controlled fixed time delay in relation to the original trigger pulse as shown below. Okay. And again, all I'm saying here now is this monostable multivibrator waveforms, varying the values of the capacitor CT, the resistor RT, or both can change the time constant of monostable multivibrators. Okay. Monostable multivibrators are generally used to increase the width of a pulse or to produce a time delay within a circuit, as the frequency of the output signal is always the same as that for the trigger pulse input. The only difference is the pulse width. and you can see what I mean in a moment in regards to the pulse width. Now here I can have negative trigger pulse, okay? We can have a short time constant in regards to the pulse width, so that's a short time constant. Or you can have a longer time constant. Now this time constant here can even be longer than this, or it can even be shorter than this. Okay, so bear that in mind. But that is dependent upon the RC time constant is dependent upon the RC circuit that you have in place. You can modify it by changing any one of those components. By changing those components, you change the time constant. Okay, thank you. I hope you found this useful. And again, please slow down the work, draw the diagrams out for yourself, write out the text, make it for your own. Okay, take your time, do some additional research in regards to monostable multivibrators, and you will find that once you begin to take interest in these things, they are quite fascinating. I mean, I've read upon it, and I've written quite a lot of more work on it myself as well by research, and some guys have written some good books as well, and because they've actually taken the time to do experiments in certain cases using them. Now what I want to do also in due course is to show you some of the electronic circuits which can be used in regards to these type of circuits and more. Okay, right, thank you for your time. I trust you have Happy New Year to you all, okay? And I look forward to seeing you all in the new year. Bye bye for now. Let me just make sure we get to the top and that everything is in place, that you can see everything. Okay, thank you. Okay, have a good day. Bye bye.